Hello everyone, JCE Connect. I welcome you all for this particular lecture. So in this particular lecture, I'll be deriving most economical triangular section equation. So in previous lectures, we have been discussed about most economical trapezoidal channel section, as well as we solved a few problems on that. So in this particular lecture, what are the conditions uh, for a uh, for getting a most efficient triangular channel section? So that we'll be discussing in this particular lecture. So here consider a triangular channel section. Here is a picture shows the triangular channel section of depth of flow as a y, and the angle subtended at the crust or at the sill level is 2 theta, and the side slope having this channel section is z horizontal to 1 vertical, 1 horizontal to, sorry, 1 vertical to z horizontal. So here given, consider a triangular channel section with side slope 1 in z, means 1 vertical, z horizontal, with depth of flow y as shown in the figure. So just look at the figure shown here. The depth of flow is a y and the side slope as 1 vertical to z horizontal. Then how the flow area can be given here? So here the flow area A equal to z y square. Flow area is z y square. So it, in terms of trigonometrical function, the flow area can be written as y square tan theta. Then how this particular z y square comes? Uh, just you look at this figure here. So this is a triangular channel section, this one. In this one, this is the free surface of water, and let us draw one perpendicular. This total angle is 2 theta, and this angle is with theta, and this angle will be theta. Then side slopes are given z horizontal to 1 vertical. So for 1 vertical, z is horizontal. I hope you are understanding. For 1 vertical, z is horizontal is given. Therefore, for y vertical, let us take x as a horizontal. Means this one. X cross multiply. When you cross multiply, you will get x equal to z into y. I'll repeat once again. See, for one for one vertical, z is horizontal. So for y vertical, x is horizontal. Let us take this as a x. We don't know this distance. Let us take this as a x. So just cross multiply. When you cross multiply, you will get x equal to z into y. So this value will be z. This one we get z into y, and also this also z into y. Now calculate area of one triangle. Area of one triangle is half. Now base is what? ZY into depth is y. What do we get? We get half z y square. But there are two triangles, triangle 1, triangle 2 here. So just multiply it by 2. 2 to get cancels. You will be getting z y square. The same I written here, z y square, area of flow. I hope you understood this one. So here area of flow is z y square. But this is in terms of depth of flow. The area of flow is written, it is in terms of depth of flow. But in terms of trigonometrical function, so flow area becomes y square tan theta. How this tan theta comes? Again, look at the figure. So in this figure, the angle subtended at crust level is 2 theta. This angle is theta. This angle is theta. Then what is tan theta? Tan theta is opposite by adjacent. That is opposite is zy. Adjacent is how much? Y. This is y. This is adjacent. And this is opposite. Opposite by adjacent. Zy by y. It cancels. Then z equal to what? Tan theta. Okay. So in place of z, I have substituted tan theta here. Hope you understood this one. So y square tan theta. Then the perimeter. So perimeter here I written P equal to 2y root over 1 plus z square. That is in terms of depth of flow as well as side slope, this perimeter. Also in terms of trigonometrical function, it becomes 2y sec theta. So how this 2y root over 1 plus z square comes? So again the same thing. Just take this one. This slant length, calculate the slant length. This one. This is a triangle and this is 90-degree triangle. This side you are knowing zy, and this also you are knowing vertical length also you are knowing. Then Pythagoras theorem, from this you will get y root of 1 plus z square. Then there are two sides, this side as well as this side. Then it is 2y root of 1 plus z square. So that becomes vectored perimeter. P equal to 2y root of 1 plus z square. But we know the value of z as tan theta. So substitute that tan theta here, it becomes root of 1 plus tan square theta. So 1 plus root of 1 plus tan square theta will be sec theta. So root of 1 plus tan square theta will be sec theta. Okay, I hope you understood this one. So that is the same thing I written here, 2y sec theta. Then from the flow area, just you take y equal to root over a by tan theta. Then substitute in perimeter equation. This becomes like this. Then as we know, if channel to be most efficient, the perimeter should be minimum. Wetted perimeter should be minimum. For minimum perimeter, dp by d theta equal to 0. So in rectangle and trapezoidal channel sections, we have differentiated with respect to depth of flow. Here we are differentiating with respect to angle theta. Again, in this case also we may differentiate with respect to depth of flow. That case I'll take next. We'll get the same answer. So this the depth of flow, it depends upon the angle subtended at the crust. Here, this one, depth of flow. Okay. So here again, the for a minimum perimeter dp by d theta equal to 0, because perimeter depending upon the angle theta. So with respect to theta, we have to differentiate the wetted perimeter. So wetted perimeter equation, we are having this equation differentiate with respect to theta. So you are very good in differentiation and all. You differentiate, use u by v formula, differentiation of u by v formula, then differentiate this one, this equation you differentiate, and after differentiating you will be getting this one. Just differentiate, you will get this one, you will get this one. Then I hope you are understanding. Just to differentiate this one with respect to theta. Then next, when you differentiate with respect to theta, these are the steps you need to follow. Just go on differentiating trigonometric functions. So finally you will be getting uh, this one, theta equal to 45 degree. It means for a most efficient triangular channel section, the apex angle shall be 90 degree, or right angle triangular channel section. This theta is for one angle. This is a triangular section. So this one theta. So for one side this is 45 degree and this is 45 degree. So it will be a 90 degree. So hence for a most efficient triangular channel section, the apex angle shall be 90 degree or right angle triangular channel section. So that conveys the maximum discharge. So this is the derivation of triangular channel section. So it's a very important for the examination point of view. So please practice this problem, and for a most efficient triangular channel section, the apex angle should be 90 degree or right angle triangle to convey maximum discharge. So when it becomes a 90 degree right angle triangle, then the side slope becomes 1:1. 1:1. Okay. Then the efficient hydraulic radius can be given as A by P. So area by weighted perimeter, substitute the values obtained. So you will be getting y divided by 2 root over 2 root 2. So that is the answer. So this is the answer. Just go through this one. Most economical triangular channel section. This is the derivation, the very simple. First you have to calculate the flow area, then you calculate the wetted perimeter. Then for a most efficient channel section, the wetted perimeter should be minimum. Then differentiate that perimeter with respect to theta or with respect to y. You will be getting the most efficient triangular channel section conditions. So here the condition is the triangular channel section should have a apex angle 90 degree to get the maximum discharge. That is the condition. And hydraulic radius is y divided by 2 root 2. So this is the derivation for a most efficient triangular channel section. Next. So one more way of solving this problem is in terms of depth of flow. So in previous case, in this case we have solved in terms of trigonometric function, that is theta. Again, theta is a function of depth of flow. As the theta varies, the depth of flow varies, or the y varies, the theta varies here. Okay. So next, one more way of solving this problem is in terms of depth of flow. Here given, I'll read it. Obtain an expression for hydraulic radius for hydraulically efficient triangular channel section in terms of depth of flow. Here given in terms of depth of flow. The same triangular section what I have been solved previous. This is a triangular channel section. This is the depth pre-surface of water, and they have marked this as a depth of flow y, and the side slope here that taken m horizontal to 1 vertical, or you may take a z horizontal to 1 vertical, and angle subtended is a 2 theta, but we need to get a condition in terms of depth of flow. So in previous case I have taken in terms of angle, that is trigonometric functions we have taken. Then consider triangular channel section as shown in the figure. Let the side slope of the channel be m horizontal to 1 vertical, and also let the depth of flow be y. Then calculate the flow area. So as you know how to calculate the flow area, it has two triangles. Then calculate the area of one triangle that is half base into height, half base into height. Then this will be the base. Calculate this base because having a side slope m horizontal to 1 vertical. So and calculate this horizontal length. Calculate the area of one triangle, multiply it by 2. You will be getting this one, half my square. This is for one triangle. Flow area of the channel, that is the total flow area of the channel, it will be 2 times of this triangle. You will be getting this answer, my square. Then m will become a by y square. Then calculate wetted area. So calculate wetted area of the channel. Wetted area of the channel will be AB plus BC. That is 2AB. Then one side slant length. You know how to calculate this slant length. Apply Pythagoras theorem here. You will be getting one side slant length. Then you will be getting this one. I hope you are understanding this one. It's a simple. Try to understand this derivation. This in exam they may ask in terms of trigonometric function. If they are asking in terms of trigonometric function, you will be getting theta 45 degree. Even if they ask in terms of depth of flow also, the angle you'll be getting a 45 degree at end. So again you substitute all the values in the perimeter equation. Then since the condition for hydraulically efficient cross section, hydraulically efficient section, I'll repeat, since the condition for hydraulically efficient cross section is the minimum perimeter for a given flow, means the wetted perimeter should be minimum. That is, differentiate dp by dy equal to 0. Then when you differentiate this wetted perimeter with respect to y, in previous case we have been differentiated with respect to theta. Here you have to differentiate with respect to y. When you differentiate with respect to y, finally you will be getting m equal to 1. M equal to 1. When that m equal to 1, we are getting m equal to 1. So it means tan theta equal to 1. So tan theta equal to 1 means it's a 90 degree. Tan 90 equal to 1. Okay. So wetted perimeter of the channel will be P equal to 2 root Y. Then hydraulic radius of the channel is, calculate R equal to A by P. Again you will be getting in terms of Y, that is depth of flow. So this is about the derivation of hydraulically efficient triangular channel sections. So the derivation I have discussed in terms of trigonometric function. So finally you will be getting a theta 45 degree 1 theta, and the apex angle should be 90 degree. So if they ask in terms of depth of flow, so instead of differentiating wetted perimeter with respect to theta, you have to differentiate with respect to y here. When you differentiate with respect to y, you will be getting the value of m equal to 1 you will be get. Again perimeter also you will get in terms of y, hydraulic radius also you will get in terms of y. I hope you understood this derivation. Please practice these derivation and try to understand. These are very important for the examination point of view. Thank you.